Greetings to the respected faculty. I am Lasya Mandapati from CSC AI and MLB section. My roll number is 24951A6686. And today I'll be presenting the topic titled Medium Generator for Case Studies on ISA Design. This project combines both theoretical and practical aspects of computer architecture, focusing on designing and analyzing instruction set architectures in a controlled and educational framework. The main idea behind this project is to build a medium generator that can automatically create more balanced and moderately complex instruction sets, also known as ISAs. In simple terms, the tool generates examples of instruction formats and architectures that are realistic enough to study but not as complicated as industrial grade ISAs like x86. The purpose is to help students and researchers understand instruction encoding, addressing modes, and performance trade offs in processor design without needing to access the expensive framework or complex simulators. One of the main challenges in teaching or researching ISA design is that existing examples are either too simple or too advanced. On one side, you have textbook level examples like small RISC or RISC processors, which are easy but don't show real design trade offs. On the other, industrial ISAs like x86 or ARM are too detailed for beginners to fully understand. The problem statement here is simple. Can we create a system that automatically generates ISAs of medium complexities that are not too simple, not too complex, which can be used for case studies and classroom experiments? This is what my project, the Medium Generator, aims to solve. The objectives of the project are threefold. First, to design a medium generator tool that can generate ISA examples automatically based on configurable parameters. Second, to allow users like students or researchers to analyze these instruction sets, studying aspects like opcode width, instruction types, and addressing modes. And third, to integrate both theoretical ISA principles and practical experimentation, which provides a platform that can be used both in teaching and in small scale research projects. Before we go into system details, let's quickly recall what an ISA actually is. Set architecture or ISA is the interface between software and hardware. It defines the instructions that a processor can understand and execute, such as add, load, store, or jump. The efficiency of a processor heavily depends on its ISA design. For example, how compact the instructions are, how many addressing modes it supports, and how fast they can be executed. In this project, I explore these design factors by automatically generating sample ISAs and analyzing how design decisions affect performance and complexity. Essentially, this work simulates what ISA designers do at the architectural level, but on a smaller, controlled scale. The medium generator system works in a few simple steps. First, the user defines a parameter, like the number of instructions, opcode width, and addressing modes. Then, the generator classifies instructions into categories such as arithmetic, logical, data transfer, and control flow. Next, it assigns binary opcodes and addressing modes automatically, creating a balanced ISA table. Finally, the output can be tested in simulators like RARS, RARS, or Logisim, which visualize instruction much better. This makes the generator an effective bridge between ISA theory and real hardware simulation. The methodology followed a structured six-step process. Number one, specification phase. Defining the ISA's core parameters, number of instructions, opcode width, etc. Design two, generator design. Developing a Python program that constructs the ISA automatically. 3. Simulation environment. Testing and validating the generated ISAs in simulation tools. 4. Evaluation metrics. Measuring encoding efficiency and instruction density. 5. Validation. Comparing with standard architectures like RIC RISC-V or MIPS. Documentation. Recording results and preparing case studies for academic use. Tools like Python and Logisim were used because they're lightweight, often open source, and easy to integrate. And to my right, you can see the code used. I like to mention that the code helps automate case study creation for different ISA configurations. Now, the practical implementation is done using Python. In the script, it is I first defined instruction categories like arithmetic, logic, data transfer, and control. Each instruction gets a 4-bit opcode and a random addressing mode such as register, immediate, direct, or indirect, which we'll look into in the next slide. The script then generates a format table displaying the instruction, its opcode, addressing mode, and a short description. For example, add might be registered as opcode 0001 with register mode. This makes it possible to automatically generate different ISA sets every time the code runs, giving endless combinations for case studies. Here is a sample of the output table produced by the generator. It includes instructions like add, subtract, multiply, divide, load, and store, each with unique binary opcodes and addressing modes. For example, as you can see here, the instruction add has the opcode 0001 and an addressing mode register. The instruction load has an opcode 0101 with an immediate addressing mode. This table can be easily exported, analyzed, or fed into a simulator to observe actual instruction execution. It demonstrates the generator's ability to create ISA examples that are both functional and educational. After running the generator multiple times and analyzing the outputs, I found that it consistently produced balanced instruction sets with a medium level consistency and complexity, typically 10 to 20 instructions. Each instruction had unique opcodes and addressing modes confirming correct functionality. The generated ISAs showed realistic encoding density and opcode distribution, making them highly suitable for performance analysis or for comparing RISC RISC or CIC CISC design philosophies. This approach has several advantages. It simplifies ISA learning by letting users generate and test their own examples. It bridges the gap between simplified textbook ISAs and complex real world designs. It can be customized for research or teaching purposes. And mostly, it provides a hands on experience in architecture design, which enhances learning compared to purely theoretical approaches. It's efficient, practical, and extendable for future development. To conclude, this project successfully developed a medium generator for ISA design, combining the theoretical understanding with practical implementation. It helps students and researchers understand ISA structures, encoding methods, and performance implications through interactive case generation. In the future, this project could be extended by adding 1. A graphical user interface or GUI for easy operation. 2. AI driven instruction optimization. 3. HDL support for hardware synthesis on FPGA. And Compiler 4. Compiler integration to execute simple programs on generated ISS. With these additions, the generator could evolve into a complete educational platform for ISA design and simulation. Thank you for your attention. That concludes my presentation on Medium Generator for case studies on ISA design.